I'm Anil Kumar. Welcome to my series on independent events. I will consider this to be a next level of independent events which we are going to discuss. We'll begin with very simple cases. We'll try to answer these four questions one by one. Question number one here is, what are mutually exclusive events? Question number two, what are independent events? Question number three, true or false? Independent events are mutually exclusive. Question number four is, in a family with three children, consider the following. We have three different kinds of events. Event P is three boys or three girls. Event Q is at least two boys. Event R is at most two boys. Now you need to answer this question. Which pair of the above events are mutually exclusive? And second part is, which pair of the above events are independent or dependent? You can always pause the video, answer the question, and then look into my suggestions. The whole idea of revisiting mutually exclusive and independent events at this stage is to answer question number 4. So that is the target for us. We need to figure out which two events are independent and which two events are dependent, right? So that is the key issue. Let us begin with a very basic definition of what we have learned so far of mutually exclusive events first, right? So question number 1, we say mutually exclusive events. We are talking about events like even or odd numbers, right? So these are mutually exclusive, nothing common, right? We also represent these events with the help of Venn diagrams. We say, well, if we have the events kind of like this, and the two events are kind of like this, they are mutually exclusive, right? So these are mutually exclusive events. What you note here is that we are looking into subsets, and the other critical number is, do we have anything in common? Do you see that? So when you are answering these questions, you're trying to figure out whether the events are mutually exclusive or not. Is that clear, right? So you'll also realize that you learned mutually exclusive even before discussing about probability, right? So there is no reference of probability when you talk about mutually exclusive events. Am I clear? It is a very important context, and that's why we are revisiting. Mutually exclusive are the events where nothing is common between those events. Two or more events are mutually exclusive. The third event could be kind of like this, right? Nothing is common. Now let's talk about independent events. What we explained was that, let us say if we have some red balls and some green balls, so we'll take up the examples which are so common, repeated all the time. Let's say we have 5 red balls and let's say 6 green. And in that case, we are talking about two scenarios. Scenario 1 and 2, they are with replacement, and the other is without. Now what happens? So these are the two scenarios, with replacement, without replacement. We are checking one thing, and that is, does the sample space change? That is the question we ask. We also ask a question, is probability same or different? Now, based on these questions, we decide whether it is independent event or not. Do you see that? So, if you compare these two parts, in independent events, we are not talking about subsets. In mutually exclusive events, we are not talking about probability, right? Of course, later on we did connect. Let me add that part also here. We say probability of event A or B is equals to probability of event A plus probability of event B minus probability of event A and B, right? So we talked about probability later, and we say when the sum of probabilities is same, it is mutually exclusive. We later connected, but that's not critical, right? The critical is subset. Here we're looking at the probability, and in simple examples we could say that if probability changes, that is, with replacement, it does not change. Without replacement, it changes. So we say this is dependent and this is independent. Does it make sense? That is what we learned. Now, let us look into our question number 4, which is, in a family with 3 children, consider the following. Event A, 3 boys or 3 girls. Event Q, PQR, at least 2 boys, and R is at the most 2 boys. Can you answer this question? Which of these pairs are independent and which are dependent? From our definition so far, we are unable to answer this question. That means something is missing. The missing part will be discussed in this particular video, and let me talk about it now. For independent events, we are always looking into the probability of 2 events. Let's say we'll consider A and B, we can consider. So A intersection B. If this event is equal to probability of A times probability of B, then we say they are independent. Is that okay? And if they are not equal, that means if the probability of A intersection B is not equal to the product of A and B, in that case we say dependent. Is that clear? So that is our new definition of finding out whether the events are independent or dependent or not. Is that clear to you, right? So that is the beginning, and now I think we have understood what are mutually exclusive events, what are independent events, and then this question, true or false, dependent events are mutually exclusive. The answer is false. As we can see that their context is different. No way they are kind of related. Do you see that? So if some event is not mutually exclusive, it could be independent, right? Now we'll take up the example and show you how that can be proved, right? So let's move forward and discuss it in more details. Actually, I've already answered this particular question. That is, what are mutually exclusive events, what are independent events, and whether this statement is true or false, right? But we can come back to this later. Let's take example 4, which is, in a family with 3 children, consider the following. Event P is 3 boys or 3 girls. Event Q is at least 2 boys. Event R is at most 2 boys. which pair of the above events are mutually exclusive, and which pair of the above events are independent or dependent events, right? So we'll discuss this and then we can get back to our question number 3. I hope that makes sense, right? Okay. So in a family of 3 children, what is the sample space? The sample space for us is all 3 could be boys, so we can write this as all 3 boys, right? Or it could be, let's say, first 2 boys and then a girl. And we could have 1 boy and then we could have a girl and a boy, or we could have the first boy, girl and a girl, right? So girl and a girl. So these are 4 combinations with starting with boy. With girls, we could have 1 girl, all 3 girls we could have, okay. And we'll go in this order. 2 girls and a boy, girl, boy, girl, or it could be girl, boy, boy, right? So anyway, you'll get 8 combinations. That's very clear to you. That's the sample space. When we say event P is 3 boys or 3 girls, let me write this event P as 3 boys is this, 3 boys. Is it okay? 3 boys. Event Q is at least 2 boys. So that means 3 boys will work, right? At least 2 boys means 2 or more. This is also good. Boy, boy, girl. Boy, girl, boy is fine. So at least 2 boys. So we get the last combination, which is girl, boy, boy. At least 2 boys. Now the last one here are, let's look into that, are, which is at most 2 boys. That means 2 or less, right? So this will not work. So we could have 2 boys and a girl. We could have boy, girl, boy. We could, this will not, at most means 1 will is okay. 1 boy, 2 girls. All girls is also fine. 2 girls and a boy, girl, boy, girl, and girl, boy, boy. So all this will work, correct? So what we see here is event P has only, 2 elements, 3 boys and 3 girls. So, okay, I made a mistake here. Even this is correct, right? 3 boys and 3. There are 2 elements in this. In Q, there are 1, 2, 3, 4. In R, there are 1, 2, 3, 4, 5, 6, 7 elements, right? Now let's talk about mutually exclusive. So if I consider event S and P, we can write this together also, S and P. In that case, what is common between, in P and Q? So let's consider P and Q, okay. We want to see if we have mutually exclusive events or not. See, if I consider P and Q, we have boys common, right? 3 boys common. So since we have something common, we are clearly seeing that this is not mutually exclusive. Okay, now let's consider the next one, which is, let us say, P and R. So in P and R, we have a common element, which is girls. So that is also not mutually exclusive. And if we consider the third set, which is R and Q, in R and Q, we have quite a few common, right? So it is at the most 2, and here we have 2 for 3. So these 3 are common. So R and Q, the common elements are BBG, BGB, and GBB, right? So we see that none of them are mutually exclusive. So we get none of them is mutually exclusive. Is that clear? So we have answered this question. There's something common, so none of them is mutually exclusive. Now, can we conclude from here that all are independent? That is interesting, right? The answer is no, right? We'll show you just now. So let's move on, and now we'll check for independent or dependent events. So we'll again take the same example and discuss independent and dependent events. Now, let us answer the question based on dependent and independent events. So these are the three events we're talking about. Event P, 3 boys or 3 girls. Event Q, at least 2 boys. Event R, at the most 2 boys. Now for independent events, if we have, let's say, events A and B in general, for example, so we say probability of event A and B, if that is equal to product of probability of A and B, if this is true, then we say that the events are independent. Okay, so that is the definition, and that is the way to find whether given events are independent or not. Now this definition can be extended to 2 or more also, right? So now let's revisit this. We'll again get to the possibility of sample space. What are the combinations? So the sample space, as we just saw, was 3 boys or 3 girls. We could have 3 boys. We could have a boy, boy and a girl. We could have boy, girl, boy. We could have boy, girl, girl, right? So beginning with girls, all 3 girls could be there. And we could have girl, girl, boy. Or we could have girl, boy, girl. Or it could be girl, boy, boy, right? So that gives you 8 combinations. Amongst these 8 combinations, the event P will be 3 boys or 3 girls. That means it has 2 elements, 3 boys or 3 girls. Now what is the probability of event A? So event P. So probability of event P is 2 out of 8, right? So it's 2 out of 8, which is 1 over 4, correct? Now let's look into the event Q. So the event Q is at least 2 boys. That means 2 or more, right? So 3 boys or 2 boys, girl, boy, girl, boy, 2 boys, right? Okay. Now here it is the last one, girl, 2 boys. So in this particular case, probability for the event Q is 4 out of 8, right? 4 out of 8, which is half. The third event R, we can write at most 2 boys. That means 3 will not work, 2 or less. So all others, right? All 7 of them. So we have boy, boy, girl, boy, girl, boy, boy, girl, girl, all girls, girl, girl, boy, boy, girl, and girl, boy, boy. So all these, that is 7 out of 8, is the probability for event R, which is at the most 2 boys, right? Which is 7 over 8. Now the idea is to figure out whether P and Q are independent or not. So what we do here is that we'll see the intersection of P and Q. So let me also write down the intersection of P and Q. So what is common between P and Q? That is intersection, is it okay? So if you see P and Q, the intersection is only one element, all 3 boys. correct? And the probability of this intersection of P and Q is 1 out of 8. 1 out of 8, right? 1 out of the sample space of 8. You will notice that this intersection is actually, let's check, is it same as probability of P times probability of Q? Let's check. So probability of P times probability of Q is what? Probability of P is 1 over 4 and probability of Q is half. So when you multiply, you do get 1 over 8. So they are equal. Is that okay? So what we get here is they are equal. 1 over 8 and 1 over 8. So these are equal. And therefore, this particular event is independent. Is that clear? So P and Q, this combination is independent. Why? So let me explain you again. It is independent because the probability of P intersection Q is equals to probability of P times probability of Q. That is why. Correct? Now let's check with the other combinations. Let's say P and R. So if you do P and R intersection, then P has got these two elements. R has 4, in which R has 7, in which GGG is common, all girls, right? So the probability for P intersection R is 1 out of 8. Now let us check what is the probability for the product of P and R. Now probability of P is 1 over 4 and that of R is 7 out of 8. So when you multiply, you get 7 over 32. And you can clearly see that these two probabilities are not equal, right? Similarly, let us do the other combination, which is Q and R. So if I check intersection of Q and R, what do I get? So in Q and R, these three are common. 3 B's are not there. So we have 3 elements which are common. BBG, BGB, and GBB. Since these 3 are common, we can say the probability for this, which is P, Q intersection R, is equals to 3 out of 8, right? 3 out of 8. Now, let us check the product of probability of Q times probability of R. What do we get? Probability of Q is half and that of R is 7 out of 8. So their product is 7 over 16. And clearly, we see that probability for intersection of Q and R is not equal to probability of Q times probability of R. And therefore, these are dependent, right? So these are dependent. Right. So from here we conclude that the only independent event is P and Q. The other combinations are dependent. Is it okay? So that is how we could do it. So we found that only combination which is independent is P and Q. So I hope this procedure of finding independent dependent events from the probability makes sense. You can always extend this definition. You could always write probability of 3 events, let's say A, B, and C. If that is equal to probability of A times probability of B times probability of C, in that case we'll conclude that these are independent events. And in case this is not true, then they are dependent. So I hope that is clear, right? So now we can actually again look into the portion which we left, just to summarize. So we're talking about these three questions. We understand what are mutually exclusive events. Now, mutually exclusive events, we are only talking about subsets. As far as independent events are concerned, we are talking about probability, right? So we are talking about probability of A intersection B, and if this is equals to the product of probability of A times probability of B, then they are independent, right? And the third statement, true or false, independent events are mutually exclusive, is false. We saw in our example that P and Q were not mutually, right? Not mutually exclusive. Since they had a common element, right? They had three boys as common, right? But they were independent events. Because probability of the event P intersection Q was equal to probability of P times probability of Q, correct? So I hope we can summarize now and understand that there is no point comparing mutually exclusive and independent events, since when we talk about mutually exclusive events, we are talking about subsets. And when we talk about independent events, we are talking about probability, right? And the best way to find whether the given set of events are independent or not, we have to look for this product, right? And this can always be extended to any number of events, right? So it could be A intersection B intersection C and so on. And if the product of their probabilities is same, in that case we conclude that they are independent, else dependent events. I hope that helps. Feel free to write your comments, share your views, and if you like and subscribe my videos, that'd be great. Thank you and all the best.